You know, they say love is like a bridge. It holds, it bends, and sometimes it breaks under pressure.
Char, pero unlike sa mong love life, this bridge has support, literal jud.
Cliche ra kay ng inana dol oy, pero nakoy question. Ang sa lugar mahitabo kung ang love ang load ibutang sa specific points. More lang na siya heartbreak na gikan sa langit ba?
Simple na. As engineers, we calculate the deflection gamit ang double integration method.
Guys,
Unsa man?
kung ang gugma kay sama sa beam, kanan na lugar point load na permira jud sa usa ka lugar ang pressure. Kapaya sa akong kasing-kasing nila kutob.
Usa lagi, ayaw sa civic crush na dili mo tagad nimo. Piling pang statics, pero feeling na.
Maka-relax na tag-ahat na dol oy. Pero sige, thank you dol.
Sige, balik na sa real talk. Here's the problem of the LimKetkai. So, let's solve it using the double integration method. Come on!
Determine the maximum deflection of Ketkai's beam using the area method after it was installed with an LED screen. Use double integration method. So in solving our double integration method, we must follow steps in order to conquer it. The first step is to define the problem. So we must understand that the beam is simply supported at ends A and D. It has a total length of 30 feet equally divided into 3 segments. AB is equals to 10 feet, BC is equals to 10 feet, and CD is equals to 10 feet. A 40 key point load is applied at point B and another 40 key point load is applied at point C. The material and cross-sectional properties are modulus of elasticity, which is 30,000 ksi, and moment of inertia I is equals to 1,000 inched raised to the power of 4. So our objective here is to determine the vertical deflection Y max of the beam using the double integration method. So next up is the step 2, which is to solve for the reaction forces. So since our beam has a symmetry and equal loading, so we must understand that RA is equals to RD. In order to get the reaction at D, we must first get the summation of moment of A, and that will give us reaction D equals to 40 kips. Meanwhile, in order to get the reaction at A, we must get the summation force of Y, and that will give us the reaction at A equals to 40 kips. Moving on into our step 3, which is the moment equations for a segment. So we divide the beam into 3 regions and define moment functions based on distances from the left end, like x is equals to 0. And also, this is where we double integrate our equation in order to get our final LE. So in our segment AB, we have our moment is equals to 40x, and our double integrated LE is 20 over 3x cubed plus c1x plus c2. In our segment BC, we have a moment of 400. Our double integrated LE is equal to 200x squared plus c3x plus c4. And lastly, on our segment CD, we have our moments is equals to 1200 minus 40x, and our double integrated LE is 600x squared minus 20 over 3x cubed plus c5x plus c6. Next is our step 4, which is we apply boundary conditions. In our boundary condition 1, we have at A, x is equals to 0 and y is equals to 0. So we input that or substitute the values of our x and y into our LE so that we could get our boundary condition value. So in our boundary condition number 1, we have our C2 is equals to 0. Same process is we're going to use in our boundary condition 2. At D, x is equals to 30 and y is equals to 0. We substitute the values of x and y to our LE. That will give us the boundary condition of 2 is 30 C5 plus C6 is equals to negative 522,000. In our boundary condition 3 at B, x is equals to 10. That will give us C1 minus C3 is equals to 2000. And next is boundary condition number 4. At P is also x is equals to 10. And that will give us 6,666.7 plus C1 equals to 20,000 plus 10 C3 plus C4. On our boundary condition 5, slope at C, x is equals to 20. If we substitute the value of x in our LE, we will get C3 is equals to C5. And last but not the least, on boundary condition 6, deflection at C, x is also equals to 20. And it will give us 80,000 plus 20 C3 plus C4 is equals to 186,666.7 plus 20 C5 plus C6. And under the boundary condition, we have the summation values of C, which is C1 is equals to negative 1,000, C3 is equals to negative 3,000, C4 is equals to 70,000, C5 is equals to negative 3,000, and C6 is equals to negative 432,000. So question, how did we get the other values of C? So it is very simple. We only need to equate all the equations and substitute the already found value of C, and you shift solve, and then you get the other values of our C's. Last step is to maximum deflection. So it is where we get our objective of our problem. Before we can get the Y max of our deflection, we must first get our unknowns, which is first the x. So in order to get our x, we need to use the equation of LI BC, which is 1200x squared minus 20x minus 3000x squared minus 60x plus 150 is equals to 0. And then we will use the Caltech of our calculator's shift solve, which is we will get the x is equals to 15.4231 feet. And then we must take note that our moment of inertia is on inches, so we must convert our value of x into inches so that we will have a consistency in our EI. So 15 multiplied to 12 is equals to 185.04 inches. And next is we're going to substitute the value of our x into our EI, and we will get 6,362,484. After getting our final EI, we can now solve for our Y max, which is EI over elasticity multiplied to our moment of inertia, and that will give us Y max is equals to 0.2121 downward. That's it for our LimKetkai deflection, and always remember to check your calculations. Kay dili pwede ang love ma-fail, pati bridge makaha. Salamat sa pagtanaw, solve responsibly, and higugma intelligently.